Okay, so if we have a surface with an area of A, we have an electric field like this, and we have the normal vector n hat. The electric flux through the surface, nice job. The electric flux through the surface is, capital Phi is for flux, the area times the dot product of the electric field with the normal vector, the normal hat vectors to the area. And so this is true. This works, and there should be there's one caveat in this, and it should be fairly obvious once I say it. This only works if E dot n hat is the same, or yeah, I'll say it's the same across the entire surface. Okay. Okay. This works only if this bit in here is the same across the entire surface. If not, if it isn't, then you have to break it into smaller surfaces. It's nice. You have to break it into smaller surfaces, and break it into surfaces which each have a uniform, E dot n hat across them, and then find the flux through each of those, add them up. Smaller surfaces, and add up the flux. Okay, so for example, and this is not going to be, well, let's see. So yeah, let's just say, for example, if we have, say, a cube, and we have a uniform electric field. So now I'm going to draw a uniform electric field pointing this way. Okay. The different faces of the cube are going to have different values for the E dot n hat, right? Because the electric field might be uniform. Okay, so I'm showing this here is my uniform electric field, the E, but your n hat is going to be different. For example, this one is going to have n hat that direction. The top is going to have n hat going up. This one is going to have n hat coming out at you, if this is a 3D cube. So you can see how you can't just take like the whole area of the cube, like the whole surface area of the cube, the entire cube, and do this once and then multiply it by 6, 6 times, well, not 6, but you know what I mean, 6 times one side area. You have to do each side individually and add them up. Okay, so that's where this gets a little tricky. So let me show you what we're really looking for. Is you're looking for ways to make this true. Okay, you're looking for surfaces where this is true, and there aren't a whole lot, frankly. There aren't a whole lot of possible situations you can do where this can be done. Okay, so this sounds like this complicated thing we're setting up here, where you got to have your surface, you got to have your n hat, etc. But it's going to end up being what happens is this limits us to a very small universe of possible problems to ask. Okay, so don't sweat this too much, because it's gonna work out. So let me show you now. Let's say there's our okay. So let me show you now ways that E dot n hat can be the same. Well, so let's look at the ways we can have a uniform E dot n hat over the surface. So let me just grab. Whoops. Okay. So let me grab. I don't want that exactly either. So let me. Boy. Okay. So let's do that, and I'll miss part of the red line, but oh well. Okay, so I'm going to copy that, and then I'm going to roll down and paste it in here. Oh, perfect. Okay, so, and then all I have to do here is get a brush and pretend that this was like this all along. There we go. See, you can't even tell now, right? Awesome. Okay, so we need to find places where E dot n hat equals something constant. Okay, so what I'm going to do is we're going to go through the possible ways that E dot n hat can be constant. Now, the first way, if something's constant and this is kind of a silly thing to say, but if something's constant, there are two possibilities. One possibility is that it's constant and equal to 0. Okay? 0 is constant. 0 is always 0. So this is our first possibility. And let's look then at what happens. What are the possibilities for a dot product to be 0? Okay? So if E dot n hat is 0, that means E. So remember, we're talking about this area here, and your electric field vector points in some arbitrary direction, and your normal vector is perpendicular and has a magnitude of 1. So the dot product is you take the magnitudes of the two vectors, multiply them together, and multiply by cosine of the angle between them. Okay, so just to give you an idea, this angle here is what we're talking about. I'm going to call that theta. So that's the angle between the electric field and the normal. So this is another normal here, just perpendicular. You know what I mean? Okay, it's just not here. It's the same thing though. Okay, so this is going to be equal to, this will be E cosine theta equals 0. Okay, so if E cosine theta equals 0, what are the possibilities there? Well, one possibility, of course, is that E equals 0. The magnitude of your electric field equals 0, right? And that should be obvious. I mean, if you have no electric field, you're not going to have any electric flux through the surface. That's obviously the easiest way for this to be 0, okay? The other way for this to be 0, well, the normal vector always has a magnitude of 1, right? That's why we didn't put its magnitude in here, because it's a unit vector. It's always got a magnitude of 1. It can't have a magnitude of 0, so that's not an option. But cosine theta can be equal to 0, right? Cosine theta could be equal to 0, and then no matter what the electric field is, if cosine theta is 0, then this whole product is going to be 0. Well, what are the options for cosine theta to be 0? One possibility is it can be a 90-degree angle, right? If theta is 90 degrees, the cosine of 90 degrees is 0, and the other one is negative 90 degrees, okay? So what this means is you can have a 0 flux no matter what your electric field is. You can have a 0 flux if the field is going perpendicular to the normal vector, which means it's going parallel to the surface. So the other possibility is E is parallel to your surface. Okay, so what we've done now is we've identified two possible ways that E dot n hat can be constant. And we haven't used them all up yet, okay, but I'm just outlining them with these beige to sort of highlight them, okay? So possible ways E dot n hat can be constant. The first way is for E dot n to be equal to 0, okay? And we've explored that here. So now I'm going to go back up to here and say, okay, what if E dot n hat equals some constant that is not 0, okay? So this is our other possibility. We've explored this. Now we need to know, fine, suppose we know that it's not 0. Unfortunately, it's not 0. What are the possible ways in which it can be constant? Well, one possible way, so let's look and see again that what this means is this E times the cosine of theta equals a constant. And so pretty much the only way this can be true, I mean, you could have a surface where cosine theta is changing and E is changing, but they're both changing in such a way that they always multiply out to the same thing. That's a very weird, tricky thing to look at, okay? And we're not going to do it. I don't even know how that would work. That's freaky. So what we're going to look at is going to be the most common case of this, which is where E is constant and let me do that, and theta is constant. Okay, so this is our third possibility. And the easiest way for this to be true is to have some surface, is to have a field that is, well, so let me put it this way. If this is true, theta's got to be some constant, and cosine theta has to be constant. And the most common situation for that to occur in most common situation for that to occur in is where theta equals 0. And that means that the electric field is perpendicular to your surface. So I've blocked out the top of this chart now, unfortunately, but these were the cases where E dot n hat equals 0, and the possibilities are where E equals 0 or where E is parallel to the surface. And then this is the other possibility where E dot n hat is not 0, but it is constant. And the most common case there is for E to be constant and theta to be constant. Okay, so let me sum this up now and try to get this back together with our electric flux definition. So that was not what I wanted at all. Okay, so let me plop down. Ah, come on, you kidding me? I hate it how the one click gets you way too much. Okay, so I'm gonna take this one more time because I want to make a nice little thing here, and ways for this to be true. Okay, hold on. Okay, brushes, there we go. Now I've got a brush. And no, now I'm not. Come on. There we go. Okay. Ways, actually I'll call this, I'll call this common ways for E dot n hat to be constant. Okay, I'm going to write this down for reference. One is where E electric field is 0. Okay. 2, and then in that case it's 0. 2 is where the electric field is perpendicular to the surface. And 3 is where the electric field is parallel to the surface. And in fact, you can really even generalize and say these are really cases of the same thing where the angle is constant. Okay, so that's sort of your fourth possibility, and where its magnitude is constant, and magnitude is constant for this as well. Actually, no, sorry, it doesn't matter for this one if the magnitude is constant, because if you're perpendicular, wait a minute. Oh, I'm messing this up all over the place. I'm sorry. It doesn't matter for this one if he is constant, because it's parallel to the surface. This is where it equals 0. Okay, I think I've rambled enough on this, but we're going to look, I'm going to show you then how we apply this to some simple geometries, 3 different simple situations with charge to find electric fields. And so that will be the next video.